So I think we stopped a little bit farther than neural language models. We already looked at trigram models with this sections last class, but I'm going to do a quick recap of some of the things that we talked last class first, and then we'll start today's lecture materials. So last class we looked at continuous bag of words and skipgrams, and what is related in today's lecture is the pedagogical trigram model of neural language model that we looked, how we trained it, and we looked at this example and how we can train a trigram model using stochastic gradient descent. And this was basically showed the basic, the cross entropy loss, which we'll also encounter today. And just as a reminder, the cross entropy, our loss function, is the cross entropy loss over here, where we are trying to minimize the corpus probability and our model prediction probability. So if M is our model, then then our model is predicting PMC. This is our model prediction. And the cross entropy loss is being calculated on the ground truth, which is our C, and our model, which is M. And we usually call this cross entropy, the way historical reasons, we say it as perplexity. Perplexity, the lower the number, the better our model is. We want to be less uncertain. We want to be less perplexed in general. Okay? And yeah, so we talked about that. What is the problem of such pedagogical neural language model? One of the main problem was that the large number, the vocabulary size, and the need, the memory requirements to train such large models. So before that, we talked about how we can circumvent the bottleneck problem using. There are a few techniques. We only talked about the hierarchical softmax. And the hierarchical softmax, essentially the idea is that instead of taking a softmax over the entire vocabulary, like this is a normalizing constant at the bottom, that in our original softmax function, that is going over the entire vocabulary. So this is computationally infeasible, so we want to break it down into something more feasible, and that is the idea of hierarchical softmax, where we factorize the probability of our output word, given our input word, into the probability of the bin where the output word may be, given our input word, and then the probability of the output word given the input word and our bin. And one important question is that how do we do this binning? And there are a few ways to do this binning, but it could be something heuristic and simple, such as like by the frequency of occurrences of words. And you can bin the words that C1 is the top 5% of words by frequency, C2 is the next 5%, and so on. Okay, and then, so with that, we'll move on to today's lecture. And before we do that, again, a quick logistics from the current, for the course. The assignment is due this Friday, and the assignment 2 will be released the next day, like February 11th. Yeah, I encourage you to provide any feedback of today's lecture. And also, this is missing the office hours. So we have office hours on Wednesdays from 12:30 to 1:30. The Zoom link is posted on Quercus. So please use the office hours if you have any questions about the lectures or even the assignments. Okay, so today we'll shift gears and we'll talk more about modern neural network architectures that are used in practice, like recurrent neural networks, LSTMs, and deep contextual word embeddings. So we've looked at word embeddings in previous class, and today we'll look into contextual word embeddings. Before talking about recurrent neural networks, I think it's better to give a motivation of why we actually need a recurrent neural network. So if you recall from, I think, second lecture, you know about statistical language modeling. So statistical language modeling, the idea is that you have a current word. You try to predict the probability of a current word given the previous window of words. And in order to do so, we do a simplifying Markov assumption, which is saying that our current observation depends on a certain number of previous words. Okay, so as shown in this equation over here, if we set what is the probability of word n, if we set L equals to 3, then we actually get the trigram model that we have seen previously. So word I given I minus 2 and I minus 1. And you have also seen, I think in assignment 1, you have also seen like, bigram models, like the previous word, and unigram models is just the corpus probability. What is the probability of a word given our entire corpus? You just take the count, and you've done this in A1. And yeah, so that is statistical language modeling. Now, the problem with, and we know that, again, from second lecture, that the higher the n-gram count, and with smoothing, it will improve the performance, meaning that when we're predicting what the current word is, if I give you the previous 2 words, it will be a better performance or better prediction than if I just give you the previous word. Similarly, like if I give you the previous 4 words, then you'll be able to predict the current word even better if trained on a corpus. But there's a problem with that. And this is what you may have also seen in assignment 1, that if you have the more n-grams you have different combinations. The combinatorial explosion of different possibilities of words will increase as you increase the number of n-grams. And this is a computational problem. This is not computationally feasible. So this is where the recurrent neural network intuition comes in. The motivation is that, if we can, instead of like, in the trigram training, we were using a different set of weight parameters for each of the bigrams, which is very expensive. So what if we can just use the same set of weights for all our words? So we'll look at the words, and then we'll only update the same set of weights for everything. And then we don't have to, if you can do that, then our memory requirement will scale with the number of words instead of the number of combinations of n-grams. So if you have a sentence, the cat sat on the mat or whatever, and then it will just like, we just need to have a weight, and we'll just look at each of the words. And then the longer the sentence is, the more like, the memory requirement will be dependent on the size of the sentence instead of the number of combinations of words. And we also want to condition our neural network on all previous words. And how can we do this? And this is where the idea of like a feedback connection or recurrent connection comes into play. So on the right-hand side, you can see a role representation of such a structure where you can see recurrent connections to the previous time step. And on the left-hand side, you have a computational graph of a single word or single time snapshot to show the learning process. So, so you have your, let's say, a current input word, sat, and you take, the vector representation, and then you calculate your hidden state, and this is where the recurrent connection is coming. So if this is at time t, you're calculating hidden state t, and you have a recurrent connection that provides you with the hidden state from the previous time step, which is ht minus 1. And then you use this to predict your model prediction, y hat. And then you have your ground truth prediction. Let's say it's something else, hat, not sat. And then you calculate the loss based on your loss criteria. We're going to use cross entropy loss, but whatever the loss function is, doesn't matter. So, and then you calculate whatever the loss is, and then you backpropagate that loss. And that loss like updates this weight embeddings over here or weight matrix over here, and that's how the learning happens. This W's actually shows the different weight matrices. So this is HX is basically the weight connections between X and H, and so on. Okay. So that's it. Like that's basically it. Like if it could be a feed-forward network, and this recurrent connection is the new addition. So if we do this like this, then we can have the same network applied or unrolled at each point in a time series. What it means is that we can maintain this weight sets over here. We don't need to change it. We have our 3 weight matrices, and we basically keep them the same, and we just instead sat, and then we just make the words go one step at a time, and we just basically update the weights as we see more words. And this can be, and you have whatever your downstream task is. So in your assignment 1, you had, I think, a task called POS tagging or part of speech tagging. So let's say you can say that I want to train an RNN model for POS tagging. So you have your training data, you have a bunch of sentences that like, you corresponds to, like, proper noun, lovely is adjective, and person is noun, and things like that. Or it could be a translation task where instead of you have like a foreign language, let's say it's French, and then your output is the English word for it. So whatever your downstream task is, you just basically go ahead and train it for that. So here, sorry, is there a question? Okay. So here, let's take a one-time snapshot for the RNN. Some of it we have already talked about in the previous slide. So here, again, here we have a concrete example with the word, input word as where, and our prediction is approaching. And basically, again, you have the word embeddings here. So at a single time step, I want you to really understand the way we get our hidden state. So G is any activation function. So what's happening is that we have our previous hidden state, and this is coming from, and the corresponding weight is WHH. And we have our current input, which is basically corresponds to where, the embedding for where, and the corresponding weight matrix is HX. And this is our activation function, and then that's how we get our current at time step t, the hidden state embedding vector. And in order to, y hat is our prediction, and so we then multiply our hidden state, current hidden state, with the HY word embedding or weight embedding. And then we take a softmax. Can someone tell me that why do we take the softmax at the outer layer of our neural net? Why do we need the softmax over here? Why not just this? Yes?
We're predicting probability of what output level is coming.
Yes, that's right. So we want to, like, the softmax is ensuring that the output is a correct probability, and all of them sums to 1. So that's the job. That's why you'll see that at the outermost layer, you always, like, there's output logits, and you put a softmax to normalize the output probabilities. Yeah, so, okay, so that's very good. So why don't someone tell me? So I have this thing here called equivalent notation. So what I'm saying is that this red HT and their equivalent notations, is everyone clear that why they're equivalent notations? There shouldn't be any confusion here, because you'll see this alternate notation. Actually, you'll see this notation more often in literature or, like, blogs or whatever. But you should understand that why why they're equivalent notation. So can someone explain why they're, or is there any confusion about why they're equivalent notation?
Yeah, I guess it would be useful to go.
Okay, sure. So yeah, so why don't I just do that on the board? Maybe that's a bonus for people who are attending in person. Okay, so okay, so you're okay with this, right? So I'm just multiplying the previous hidden state vector with the weight embedding over here, weight matrix here. Okay, that's good, right? This is from the first notation. And then we have current input vector being multiplied. Let's say this is a longer matrix like this. This is our weight, yeah, HX. Okay, and this is a little bit longer. So in the first notation, we're just basically doing this separately. In the second lower line, the only thing we're saying is that, okay, so now we're just going to place hidden state and the input vector side by side. Oh God, this. H t minus 1, concatenate with, so our x was a little bit longer vector, let's say, xt. And we'll concatenate the weight matrix by dimension 1. So we have one weight matrix, we call it Wi, our input weight matrix, okay? Now, what you need to understand is that when you do this multiplication, So this part corresponds to like, WHH, and this part corresponds to HX. And this multiplication over here and these two multiplications where you take each of these and then concatenate them together, they're the same thing, okay? Does that make sense?
Yeah.
Yeah? Okay. So like in the first notation, we're doing, like we're basically showing that, H times WHH, then concatenate that with X times this WHX, and then whatever the output vector. This is the same if we just say that, okay, so we have one vector, which is XT, and then we're multiplying by the embedding vector. So yeah, so you may find, yeah.
So the plus here means
Plus, yeah, that is confusing. The plus is confusing, I see that. So maybe the plus should be just a semicolon or something to, maybe this is better. This is like concatenation. Yeah, okay, good. So I think, there's some questions about like, okay, so these are abstract equations, so how do we actually codify this? So this is a very simple illustration of like the codification of what we just talked about in Python. And as you can see that, not much to explain there. This is just codification for you to see that how to, like, if there's any confusion about from abstract equations to how do we actually do this, we just do this way, okay? And we'll be doing that a lot more in your assignment too. Any questions? Okay, good. Okay, so this slide builds on the previous slide and basically talks, the dimension of our output y hat is the size of our vocabulary. So the output is a distribution, probably distribution over the entire vocabulary. And output is the word index prediction for the next word, xt plus 1. And evaluation, the reason we did a little bit of recap at the beginning of the lecture, so we're using cross-entropy loss function. So ytj is our ground truth that is coming from our supervised sample of the corpus, and log y hat is our prediction. And we basically, this is our loss. And perplexity, for historical reasons, we say we denote this using the perplexity, which is basically the cross entropy raised to the power of the cross entropy. And by doing this, we're already reduced the number of parameters from the trigram neural network that we have seen. In theory, the purpose of this hidden state with the recurrent connection is to maintain all the previous information for across arbitrary lengths of time. So, so basically, like, this HT over here should capture information about whatever the previous words were before we saw, where. And at the bottom left-hand side, you can see the two equations for RNN, calculating the hidden state and calculating our prediction. And if you see, this is very similar to just calculating these values for a two-layer feed-forward network. As stated earlier, the only difference is that now we have a recurrent connection of the previous hidden state. This is a really good blog. I encourage you all to read it. So the problem of RNNs, now the limitations of RNNs, catastrophic forgetting. So this, what we saw before, works really well if the context size of the sentence is, in general, it works okay. But in case of long-term dependencies, or if you have a very long sentence with dependencies between the different words, as the exemplified word over here, the sushi, the sister of your friend's programming teacher told you about was. And in this case, for an RNN, as you reach the last hidden state, you only have this recurrent connection, which is supposed to remember all this different subjects. But by the time you reach over here, it's likely that it has forgotten about who was talking about the sushi. Was it the friend? Was it the sister? Was it the programming teacher? So this is a common problem, and the phenomenon is called catastrophic forgetting. And now we want to look at how we can circumvent this problem. So this last layer is also like, yeah, our informational bottleneck, because it is burdened with remembering all the information of the previous hidden states. Okay, now how can we circumvent this problem? So before we talk about how we can circumvent this problem, maybe we should understand better that what's causing this problem. So here in this diagram in the middle, you can see three identical recurrent cell blocks denoted by A. And this shows basically the inner works. Essentially, this is the same. These are recurrent cell blocks of an RNN. So this is an RNN. You have XT, you have the activation, and you have the output hidden state, and you have the recurrent connection. So what happens is that when this kind of cell blocks get unrolled for a very long sequence, in order to compute the loss, you need to compute the gradient, so which is backpropagation through time. So as you backpropagate through time, if the sequence length is really long, then the gradient will either decay or explode, which is known as the vanishing gradient or the exploding gradient problem. And if you want intuitive understanding of that even better, just take any scalar that is slightly larger than 1, say 1.1, and raise it to the power 2. Or take slightly lower than 1, take 0.9 and raise it to the power 2. And if you increase the value of t, you'll see that like it's either exploding or vanishing. So that's sort of an intuitive way to look at what's happening if that time gets too long. The gradient, what happens to the gradient. So now we want to look at a technique a variant of RNN that allows us to allows gradient to flow back through time without decaying sorry, question.
Yes, so my question is, if the X is getting concatenated to the hidden state, and the hidden state gets its own weight, and so is the X gets concatenated, why would the information of X at certain time step get stored in a hidden state? They're concatenated together, right?
Happens in the weight matrix, right? So your X and the previous hidden state is updating the weight matrix. So your X is updating the weight. So that's how it's remembering.
Yeah, but the X at the next time state is only updating the X at the previous time state. How does it affect the hidden state?
So what do you mean, like?
Because they're concatenated.
Right.
So they have like separate weight for the hidden state.
So I think I see what you're asking, but think about like what we saw is a very simplified example, but you have all like in a network layer, you have connections that going through. So basically your question is that are we just updating a certain part of the weight matrix? I mean, yeah, so but you're still updating the part that updates your hidden state,
Okay.
right? And that is not getting, yeah, so, okay. So, so we want to look at, so we want to come up with the idea that allows that gradient to flow in case of longer sequences without decaying. And the way we can do this is by this variant of RNN, and we call it the long short-term memory, or LSTM. The LSTM introduce at an abstract level two clever ideas. The first idea is that this is within our recurrent cell block, we will add a self-looping recurrence of cell state, which we denote by C. Okay, so previously we already have H hidden state, recurrent hidden state, but there's a problem with that, is that the gradient decay or gradient vanishing gradient problem. But then now we maintain like a super highway of information, if you want to think about it that way, which is called the cell state, and this runs all the way across the complete unrolled chain. And the second idea is to have regulating structure called gates that allows or regulates information flow and decides what gets added to our information highway or our cell state as we go along. And on the right-hand side, so this is a gate component. So you'll see some pointwise multiplication, and you'll see a neural network layer, the sigmoid neural net layer. And LSTMs have, within our recurrent LSTM unit, we have like 4 interacting neural network layers. So the middle block over here shows the four gates that we'll be talking about in more depth now. And apart from that, we have the other stuff outside the block. They're the same as before. So we have the input xt at time t, and we have some output, hidden state output ht. And yeah, the bottom shows you the cell state, which is like a cell state is a special vector stream that runs through the entire chain and stores long-term information. And on the right-hand side, these are components of the these are components within the recurrent block. So anything that so this is just the annotation for it. So this is pointwise operation, neural network layer. This is just vector transfer, concatenation, and copy. And we'll be using this in the next slides to explain the inner workings. In itself, the gates decide. So one thing about the sigmoid layer is that you know what the sigmoid's function is. So it squashes values between 0 and 1. So you can think of the sigmoid layer as a filtering layer or a filtering gate that allows information, it blocks information. So values closer to 0 will be forgotten or blocked, and values closer to 1 will be allowed to pass. So you can also think of it as like a filter, okay? Any questions so far? Okay. All right, so the first step is the forget get layer. The forget get layer takes the previous hidden state and our current input, and then decides that which elements in the cell state based on our input and hidden state we want to keep and which we want to forget. So as an example, think of we might be remembering the plurality or singularity of our subject so that we can predict appropriately conjugated verbs. So he, she has or they have, or he is running versus they are running, right? So as soon, in a sentence, if we encounter a new subject, then we might want to forget that number that we are storing from before, because now we have a new subject, right? So this is just a pedagogical example. I mean, this is not as explicit because everything's happening in the latent embedding space, but this is an example of what forgetting could entail, right? Yeah, so essentially on the bottom left, you can see that the forget get layer output is essentially the previous hidden state and our current input, and we have like a vector of what ft, what we want to forget, and the right hand side shows like not too cool animation of what's happening. Okay, so now we know what to forget. The second step is to decide what to store. And this is decided in the input get layer. The input get layer has 2 parts. The first part is a sigmoid layer that's over here. And that takes, it takes the previous hidden state and our current input, and then it outputs and it passes through a sigmoid layer and it outputs IT, what we're calling IT. Now think of IT as a mask vector. So remember, sigmoid layer squashes values between 0 and 1. So you're creating a mask of values closer to 1s and 0s to use for the next part, which is a hyperbolic tan layer over here, which takes in the same inputs, the previous hidden state and our current input, and then outputs what we're calling as the new candidate values. So this wiggly CT over here is our new candidate values, and these are the values that we want to store from our current input and previous hidden state. So, and previously in the first step, we had calculated IT. So what happens is that we have new candidate values, and then we apply the mask to get what information of this new candidate values we want to store. Any questions? Okay. So now that we know what to forget and update, we basically update the cell state. And first we forget what we want to forget by multiplying our current cell state by the forget get output. And then we multiply, and then we write this information to the new cell state. So let's do a pictorial. Before we do, let's take a look at the equation. So first we're multiplying the forget get output with the current cell state, and then we are adding the output of our input gate layer to that cell state in order to get our updated cell state CT. Pictorially, you have the previous cell state, you're multiplying with forget get, and then you're getting a value. And then this is over here, this is the output of our input gate layer. And we're going to do a pointwise added operation to get our final updated cell state. Let's do this one more time because this is important. Okay, so you're multiplying with the output of the forget get layer. And just for pedagogy, this cell over here is a little bit lighter green, showing that some part is forgotten, so it's not as green as the other ones. And then you have the output of the input gate layer. And you do a pointwise addition. So this is something where we forgot, and this is something that we want to store. It's darker red. And we have a final updated cell state vector CT. Any questions? Okay. Okay, so lastly, we have the output and feedback. So we have our new updated cell state and how we can use this cell state to get our new hidden state and output something so that we can, use it for our purposes. So the way it happens is that we combine the output with the cell to give the hidden state. Okay. Was it instructive for me? I can try again. Okay. So here at the bottom, you can see that we have our current input and hidden state vector that passes through a sigmoid layer again. And that gives us the output, which we denote as OT. And then we multiply OT. We basically combine this output with our updated cell state by multiplying with CT. Hyperbolic tan is just there to regularize. It's a squashing function. It just regularizes CT -1 to 1. So our hidden state now, if you think about intuitively, now our hidden state has what components? It has the components of our previous hidden state. It has our current input, and it also has a bit of our updated cell state. So it has, and in some, like we have been saying that our cell state is our long-term memory, and hidden state is our short-term memory. So now our hidden state has our input, has our current input xt, has a previous hidden state ht -1, and then we also combine it with our cell state ct. So it has a little bit of everything now. Yeah.
Oh, can you normalize CT on -1, 1?
Yeah.
Why are we doing that instead of just on 0, 1?
So in LSTM, so 0, 1 would be the sigmoid layer, right? Okay. So if it's 0, then we're forgetting things, right? So we basically we use the sigmoid layer for filtering, like if you want to block something or if you want to allow something to pass. Whereas the idea of hyperbolic tan is basically it just regulates the output between -1 and 1. So it's not like that's it. It's not. The sigmoid layer's function here is as a filter, like block something or allow something to pass. Yeah, it's preserving because we don't we have our updated cell state. We don't want to throw out anything there. If we use a sigmoid layer, then some things could be thrown out. Anything near the zeros will be like going out, right? So we want to say that okay, so we have our cell state values. We want this, and we just want to sort of clip it, right? We want to clip it so that it's easier for computation and everything. So that's it. Yeah. So what state?
Like, what's the motivation for adding like cell states to our previous mode? Like, why did we
Okay, so that's what. Yeah, so that's the whole purpose of to solve the problem of long-term dependencies. So, remember the build-up that we have. The RNNs can remember if it's a long sequence, like who ate the sushi, we don't know, the subject has been lost. And then we are adding like this long-term state that sort of retains relevant, high-level relevant information. And when we're calculating our hidden state, we're combining, like we're taking that cell state and incorporating it so that our that embedding has better long-term memory, essentially. Yeah, that's the reason. Okay. So the most natural question after going through the slides would be that, okay, so why exactly like this, right? So why do we have to have these gates in this order? Why can't we have, one input gate or just the output gate, or combine this in a different way? Like, I mean, who said that this is exactly the way that solves the problem? And the answer is that it is not. There's too many variants of LSTMs. Almost every paper that uses LSTM has certain quirks or changes to the simplified architecture. So that's very common. And as an example, like this one is a bidirectional LSTM. What it does is that instead of unidirectional, it takes a sentence from left to right and then right to left, and then uses two layers instead of one layer. So I mean, the point is that high-level intuition is that the goal is to solve the long-term dependency problem so that we can retain this relative information and we don't run into a vanishing gradient problem. Now, it's worth looking at some popular variants to enhance our understanding. So here, there's one model that had peephole connections that was introduced by Jerson Schmidhuber in 2000. So the peepholes are highlighted using black. And as you can see that the difference is now each of the sigmoid layers have a connection to the cell state. And it's better if you want to see in equations, you can see that everything is the same, but the forget gate now has cell state connection, cell state value concatenated, cell state value concatenated, right? So that's the only difference. And on the bottom, there's another variant, which coalesces the forget and input gate and makes a joint decision. So before we're forgetting something and then we're storing something. So here in the bottom, it's saying that we'll store and forget at the same time. What we forget, the remaining will store or something like that. So they just couple them together. So yeah, I mean, various variants like this are possible. And the next slide, like this is a side, will not be tested, but a very popular variant of LSTM is called gated recurrent units, or GRUs. And they go a step farther, and they combine the input-output into one reset gate, and they merge the cell and hidden states. So over here, you'll see that there is no CT. They have combined the cell state and the hidden state. So you can think of GRUs as a simplified LSTM, where it's computationally better than LSTM. However, performance-wise, LSTMs perform better over like long-term dependencies, but depending on your downstream tasks, if your main goal is to improve training efficiency, you have less parameters to train, you can choose to use GRUs over LSTMs. And if you're interested in the question that, like, which of these variants are best and do these differences really matter, then at the bottom there's two papers that I can encourage you to read. Like, they do a nice comparison between lots of different variants of LSTMs. At the end of the day, the high-level result is that they're mostly the same in performance. Yes, some of the variants can perform a little better than the other on task-specific matter, like based on your task. But overall, if you take an average, they mostly perform the same. Okay. Yeah, so that's about it on LSTMs. And the last topic that I wanted to talk about was contextual word embeddings. So far, the embeddings that we have looked into, like CBOW and GLOVE, that does not take into account the context. And so before we go into deep contextual representation, I'd like to start by asking this question that if we ask that, what does the word play mean to you? So if it's asked to most people, the first thing that will come, I guess, like, I don't know, like Cristiano Ronaldo playing soccer or something, that notion of play, like physical sport. But if it is contextualized, the question with a background of like, a theater play going on, and then people would probably say, oh, the theater play. So that's exactly the case. That was when this paper came out, like Peter et al., the model is called ELMO in 2018. It really, I think, triggered the use of word embeddings the way we do in modern systems now. So the idea of ELMO is this, that instead of using a fixed embedding like we saw for each word type, it considers the entire sentence before embedding each token. So it uses a bidirectional LSTM trained on certain tasks, and outputs are softmax probabilities as on words as before. So to illustrate, think of our XT now is exhausted. And then and there's two layers. And in the first layer, we'll use a left side embedding. And then there's, on the right-hand side, there's another embedding coming from the other side of the sentence. And then the final embedding will be a concatenation of all this. So for example, like it's better if we take a look at one-time snapshot, maybe in the next slide. So each layer, if it's a L layer by LSTM, so in this previous example, it's 2-layer. Each layer computes 2L+1 representation. So where is this coming from? So XKLM is basically your representation for the word. So in this example, XK would be just the vector representation of exhausted, right? And then that is concatenated with a left to right representation. So in this case, like, this guy over here, or H1. And on the right, you'll have this right to left representation, okay? And you concatenate these three together for each of the layers. And so for each of the layers, you get a embedding for a left to right and right to left representation, and you concatenate that with X, the word representation. So that's why it's 2L+1. And then that's your now hidden state vector, or that's your representation. That is the ELMO representation. Now, this representation by itself performs well, but it's even better. The final representation is weighted on tasks. So meaning that you can have different tasks. So your downstream task could be sentiment analysis. It could be named entity recognition, and so on. So what they do is that they then fine-tune this weight even further based on specific weights, okay? And so after they do that, they have the final embeddings. So this is a one-time snapshot view. Here our running example has changed to the word play, and this is showing the 2 layers of right to left, and this is the 2 layers of left to right. And so you concatenate the left and right and the embedding of the word play, and then you multiply by the task. So here it could be like whatever the task that you're doing. Let's say that you have 3 tasks and you're weighting by tasks, and then you sum these up, and that's your vector. The final embedding is a concatenation of the actual word embedding concatenated with this ELMO embedding for that task. Okay, and so how does it help? So this table over here shows the differentiates with GLOVE. And with GLOVE, which shows for the word play, the nearest neighbors shows the regular sense of the word play, like football and games, etc. Whereas using ELMO, the differentiator is shown by, these are source target sentences instead of word, nearest sentences. So sentence 1, sentence 2. And it shows that when the sentence is specific to a game, the nearest sentence is about like the game, but if it's about some theater play, then the nearest sentence is actually about actors, fat roles it's about actors who are acting in a play, okay? And this is one illustration, and then you can also look at its performance against some of the main downstream NLP tasks like question answering, textual entailment, sentiment analysis, etc. And it showed that it had significant performance improvement over the then state-of-the-art models as baselines. And this was a very significant improvement. Yes?
Can you go back 2 slides?
Okay.
Yeah, so I don't so I understand part 2. So you're basically multiplying it by the weight for each task, and you're generating embedding from that.
Yeah. Why don't we take that question right after the class? Okay. So I just want to finish this. 4 minutes left. Oh, actually, I don't have much left. So essentially, this slide is for anyone who's interested in neural networks and language modeling research. It is a very exciting and a very expensive field. And in terms of training a model, we have many hyperparameters that we can tweak, and there's many architectures we can use. But at the same time, we have to be cognizant of our scientific skepticism, like in terms of what are our biases and expectations, and how are we evaluating the systems. So yeah, so that's all I had to talk about lecture 5. Thank you so much.